Hello everyone. Welcome back to this lecture series on Design of RCC Structures. In the previous lectures, we have studied the design of singly reinforced, doubly reinforced and flanged beams on simply supported cases using the limit state method. Today, we move into the advanced topics and a very practical one, that is the design of continuous reinforced concrete beams. These continuous beams are widely used in multi-story buildings where beam rest on more than two supports and behave differently from simply supported beams. Now, what does a continuous beam mean, sir? It's a beam that extends over more than two supports. Because of this continuity, the beam becomes statically indeterminate. So, unlike simply supported beams, internal forces in continuous beams cannot be obtained using equilibrium equations alone. And due to this continuity, negative moments, that is the hogging moments, which will develop over the supports, and positive sagging moments developed in the midspan areas. So the midspan moments are reduced, deflection is better controlled, and overall designs become more economical. Here the continuity redistributes the bending moments and improves the structural performance. So what is the importance of this continuous beam is, in real structures, beams are rarely isolated. They are a part of continuous framing system. And these continuous beams tends to reduce the bending stresses, improves the stiffness, provides redundancy and safety, whereas they require careful detailing and proper placement of negative reinforcements over support. So regarding the bending moments and the shear force with respect to the continuous beams, IS 456 has given a separate classes for the bending moment coefficients as well as shear force coefficients. Table number 12 details the bending moment coefficients for the dead loads and the live loads separately for different span conditions and different locations. If it is a dead load, means near to the middle of the end span, it will be considered as 1/12, that is WL square by 12. Whereas at the middle of the interior span, it will be taken as 1/16 is the coefficient. Similarly, at the support moments, it will be taken as negative, since the support will get the negative bending moment, that the coefficients will be taken as 1/10, and at the interior supports, it will be taken as 1/12. Similarly, the live load coefficients is also been given. And the next thing is that table number 13 details the coefficients for the shear force calculation. Similarly, dead load and live load separately at different areas. Now let us consider a numerical example to understand the design procedures. Here, we are required to design a continuous RCC beam of rectangular section with 3 spans of 6 meters each, and it's been given as an effective span. The ends are simply supported, which carries a dead load of 10 kilonewton per meter and a live load of 12 kilonewton per meter. And the grade of the material is being given as M20 concrete and Fe415 HYSD bars. We are also required to sketch the reinforcement details. This example is a typical of floor beams in framed buildings. So for continuous beams, bending moments and shear forces are determined using the moment coefficients being detailed in table number 12 of IS 456 or structural analysis methods. Due to the continuity, the maximum negative moments occur at the interior supports and the positive moments will occur in the midspan areas. Based on these moments, the beam is found to be checked. Now, let us start with the design. We'll go on with the determining the cross section of the beam. So in that case, we are assuming the width of the beam as 300 mm and assuming a span to depth ratio of 10, the effective depth of the beam will be computed as 6000 divided by 10, which comes as 600 mm. And with a 50 mm effective cover, overall depth of the beam is being computed as 650 mm, that is the capital D. Then regarding the loads, they gave the dead loads and the live loads. So starts up with the self height of the beam. The cross section has been defined as 300 mm by 650 mm. Therefore, it will be 0.3 into 0.65 into unit weight of the concrete. This is B. This is capital D into unit weight of the concrete, which will gives the self height of the beam in terms of kilonewton per meter. Next, the dead load acting on the beam is given as a 10 kilonewton per meter, and the finishing load we can assume it as 0.125 kilonewton per meter in order to get a whole number in terms of dead load. See, unlike the other beams, the simply supported beams, this continuous beams will consider the loads separately for dead as well as live loads. That's why the dead load, all the loads being combined together. So now we'll get the total service dead load as 15 kilonewton per meter, and the ultimate dead load is being calculated by multiplying the service load with the 1.5 factor of safety, which comes as 22.5 kilonewton per meter. Similarly, the live load is given as 12 kilonewton per meter, and the factored live load will be calculated as 18 kilonewton per meter. Now going on with the bending moment and the shear force, as per the table number 12, the negative bending moment at the interior supports will be computed as WL square by 10 plus WL square by 9 separately for the dead load and the live load respectively. Here the dead loads and live loads being calculated separately, and substituting all these values, we'll get the negative bending moment at the interior support as 153 kilonewton meter. Similarly, the positive bending moment has to be calculated, and that will act at the midspan area. So in which the formula will be used as WDL square by 12 plus WLL square by 10. So substituting the dead load, live load as well as the effective span, will get the positive bending moment as 132.3 kilonewton meter. Now these moments has to be checked with the limiting bending moment in order to check whether it will come under reinforced section or over reinforced section. Here the limiting bending moment, substituting the value of FCK, B is 300 and effective depth has been assumed as 600 mm. We will be getting the value as 298.08. So both the negative bending moment as the positive bending moment are lying within the limiting bending moment. Therefore, the beam is to be found as under reinforced, which is a desirable case. And in continuous beams, always require top reinforcements over the supports, whereas the midspan area, the main reinforcements will be provided at the bottom. So since MU is less than MU limit, it will be considered as an under reinforced section. And finally, the maximum shear force at the support will be calculated using the bending moment the shear force coefficient of 0.6 L. So summation of this dead load and the live load multiplying with the shear force coefficient of 0.6 L, we will be getting the total shear forces 145.8 kilonewton. Now we need to design the reinforcement separately for the negative bending moment as well as for the positive moment. Now let us design the negative reinforcement. And we know negative moments can cause tension at the top, compression at the bottom. And hence main reinforcements are placed near to the top face, and adequate anchorage will be provided into the adjacent spans. So these reinforcements controls the cracking over supports as well as redistribution of the moments. So using the annexure G 1.1, since it is under reinforced, substituting the value of the negative bending moment, we will get the AST required as 76 mm square. And checking with the minimum AST condition of 0.85 BD by Fy, we are getting that value as 369 mm square. So the calculated AST is greater than the minimum AST requirement. Therefore, we can provide the reinforcement for this 776 mm square. Therefore, providing 4 numbers of 16 mm diabars as the tension reinforcements that will be provided at the top at the support section, since it is the negative bending moment. So in which the ASD provided will comes as 805 mm square. So this negative moment or the negative reinforcement is very critical for safety in continuous beams. Next, we design the positive reinforcements in the midspan area. Here, the tension will be developed at the bottom and compression will be occurring at the top. The required steel area will be calculated based on the factored sagging moment, effective depth and the material properties. That is, again applying with the same relationship. And now substituting the positive bending moment, we will get the ASD required as 662 mm square. And already the minimum ASD is being satisfied 369. Therefore, we can provide the same number of 4 numbers of 16 mm dia bars as tension reinforcement. Now it will be provided at the bottom. Now, because we are designing the positive reinforcement and that will be provided at the midspan area. So the ASD provided will be same 805 mm square. Now we can go for checking the shear. So here shear force is maximum near supports where the cracks will be initiated. And now the shear reinforcements will be designed using the vertical stirrups. The spacing of the stirrups will be closer near the supports and can be increased towards the midspan. This will ensure the safety against the diagonal failure, tension failure, as well as the ductile behavior. Right. So the nominal shear stress will be calculated using the formula tau V will be equal to BU by BD. So substituting the values, the nominal shear stress being calculated as 0.81 Newton per mm square. Now this has to be checked with the critical or the permissible shear stress for the grade of concrete for the amount of reinforcement provided, for which first the percentage of the tension reinforcement will be calculated, which comes as 0.45 percentage, and table number 19 of IS 456 for M20 grade concrete and PT value of 0.45. The permissible shear stress in concrete has been taken as 0.456 Newton per mm square, which is less than the nominal shear stress. In that case, we need to design the shear reinforcement separately. Now, regarding the design of shear reinforcement, since it is a continuous beam and the negative bending moment will be occurring at the support section and the positive moment will be occurring at the midspan section. So, if alternative bars can be bent up at the support section from the bottom to the top in order to increase the capacity at the support section, if so, the shear carried by the bent up bars will be calculated using the relation Vs is equal to 0.87 Fy ASV into sine alpha, in which the ASV represents the area of the vertical stirrups that are going to be bent up. So in this case, let me assume I'm going to bend 2 numbers of 16 dia. We provided 4 numbers of 16, out of which 2 will be bent up near to the support in order to bring it to the top portion. So in that case, AAC will be equal to 2 into pi by 4 into 16 square. Right, and alpha is the angle about which the reinforcement will be bent from the bottom to the top. In all the cases, we can assume alpha is equal to 45 degree. So substituting everything, we'll be getting the shear carried by the bent up bars is 102 kilonewton. Similarly, the concrete itself will take care of some shear. So the shear taken by the concrete will be computed as VC is equal to tau C into B into D. So tau C has been calculated as 0.456. Multiplying with the cross-section effective, we will get the value as 12 kilonewton. So the total shear governed by both this bent up bars as well as the concrete is 180. Sorry, it should be, this one should have been 82 kilonewton. So in that case, it comes the total shear governed by the bent up bars and the concrete is 184 kilonewton. Right. So in that case, the total shear which is acting is only 145.8 kilonewton, whereas the bent up bars as well as the concrete itself will govern 184 kilonewton. Therefore, the shear is within the permissible limits. In other case, nominal shear reinforcements may be provided. So in that case, we can provide 6 mm dia 2-legged stirrups at 300 mm centers throughout the span. Now let us go with the reinforcement details for this continuous beam. The effective span has been given as 6 meter, right, in which the reinforcements are provided 4 numbers of 16 at the bottom and 4 numbers of 16 at the top, in which 2 numbers of 16 has been bent up from the bottom to the top near to the support at a distance of 900, that is 0.15 L, the cranking portion, right. So here this reinforcement details include the top reinforcements over the supports, the bottom reinforcements in the midspan, the stirrups, and the proper detailing is essential for correct force transfer, controlling the cracks as well as improving the durability. Let us summarize today's lecture. Continuous beams extend over more than 2 supports. They are statically indeterminate, and continuity procedures produces negative moments at the supports and reduced midspan moments. The design involves load calculation, moment and shear evaluation, design of negative and positive reinforcement, and finally the shear reinforcements and the detailing. So these continuous beams are a safer, more economical and widely used in RCC buildings. In the next lecture, we will continue with the advanced topics of once if the beam is being subjected not only with the moment and the shear, if it is being subjected to torsion, how the beam has to be designed. Thank you.